Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 28, and in this lecture we are going to talk about Timoshenko beam theory. So, in the last class we learnt about Euler-Bernoulli beam theory. So, in that theory we had the center line and we had assumed that the cross section is oriented in such a way that the cross sectional normal and the center line tangent, they are both aligned. So, we had only one kinematic variable, which was the deflection of the beam y. So, if we know y, we can obtain dy by dx, and which we said is equal to orientation of the cross section. Okay. So, this was of course an assumption that the cross sectional normal and the center line tangents, they are aligned, and that is Euler-Bernoulli theory EBT. But in the Timoshenko beam theory, we no more assume that, we assume that they are not aligned. So, in the Timoshenko beam theory, we again have the deformed center line, but the cross section can be something like this, okay, or it could be something like this. So, you can see for example, here the cross sectional normal and the center line tangent, they are no more the same. Likewise, over here also this is the center line tangent and that is the cross sectional normal. Okay. So, we would like to know how we can account this extra degree of freedom. So, basically now we have the deflection y as well as cross sectional rotation. Let us denote that by theta. Both are independent unknowns. Okay. So, they are independent, and we do not say that theta is equal to dy by dx. So, this no more holds here. Okay. So, we would like to derive equations for Timoshenko beam theory accounting for this extra flexibility. All right. Let us have a look at the zoomed version of this picture. So, we have the center line curve, and then at some point let us say over here we also have its tangent. Okay. So, the tangent would make an angle from the horizontal line, and that angle is dy by dx, is not it? So, dy by dx is equal to tan of the angle, right. So, this angle, if we denote this by alpha, then this is tan inverse dy by dx, right. But we assume here that dy by dx is small. So, we can approximate this with dy by dx itself. Okay. Let us then think of the cross section. So, at this point the cross section could be something like this, and here is the cross sectional normal, and the normal would make an angle of theta from the horizontal. Okay. So, this angle is theta. So, that means initially we had the cross section and the tangent. The tangent was horizontal initially and the cross section was vertical if the beam is a straight line, but after deformation the tangent gets inclined and the cross section also gets inclined, right, and this angle here is no more 90 degree. So, initially it is 90 degree, but finally it is no more 90 degree. So, what is the final angle for example? So, the final angle, so we know that this is dy by dx, correct, and the normal cross section normal, that makes an angle of theta. So, this angle is theta. Okay. So, what can we say about this particular angle? So, notice that that angle has got two parts. One is this 90 degree plus this angle, is not it? And this angle is nothing but theta minus dy by dx. So, what is the final angle? So, final angle between cross section line and center line tangent. That is equal to 90 degree plus theta minus dy by dx. So, basically the angle has increased. So, initially the angle between two lines was 90 degree, finally it becomes 90 plus theta minus dy by dx. So, the angle has increased. So, what can you say about the shear when those two lines are concerned? So, shear will be negative, right, because shear reduces the angle and here the angle has increased. So, shear here would be negative of the change in angle, right. And what shear is this? So, you see this is x axis and that is your y axis, because your beam would initially be like this and the axis is x axis and then the perpendicular is your y axis, right. So, the shear here associated with the cross sectional line and center line tangent, that would be gamma x y, correct. And what is its value? That is the negative of the whatever is the increase in angle here. So, that is negative of theta minus dy by dx, right, which is dy by dx minus theta. So, that is your shear strain, and notice also where are we measuring this shear strain. So, supposing that the cross section is rectangular, then we are measuring this shear strain at the center of this cross section, because the center line is connecting the center of each of the cross sections, right. So, gamma x y we have measured at the center of the cross section, and that is this gamma x y. Okay. Now, can we relate it to the shear force that is acting in the cross section? So, supposing that the shear force in the cross section is V and the cross sectional area is A, then what is the average shear stress? So, what is tau x y average? You see, it is tau x y because cross sectional plane is x plane and we are applying force in the y direction, right. So, it is tau x y or tau y x, but they are same. So, this becomes equal to V by A, that is the average shear stress. Now, how is this average shear stress related to gamma x y? Can you recall the distribution of shear stress in rectangular cross section, for example? So, when we had rectangular cross section, the shear stress was maximum at the center and it was 0 at the two ends. So, it had a quadratic variation, correct, and the value of shear stress at the center tau here was actually 3 by 2 times the tau average, is not it. So, that means we can find out tau x y at the center, let us say naught, that is equal to V by A, which is the average shear stress multiplied by 3 by 2, is not it. Or we could also write this as V by A divided by 2 by 3. Okay. So, 2 by 3 is called the shear correction factor. So, this is to account for the change in shear stress, all right. So, we will call this 2 by 3 as shear correction factor, and let us denote that by K, shear correction factor, and this number will be different for different cross sections. For rectangular cross section it is 2 by 3, for circular cross section it turns out to be something else. So, finally, we have tau at the center x y equal to V by K A. So, what would be gamma x y at the center? That simply V by K G A, is not it. Shear stress is equal to G times shear strain. So, we have to divide by G to get shear strain, but this is also equal to, which we just figured out, is dy by dx minus theta, correct. So, this number here comes from over here. So, this gives us one equation of Timoshenko beam theory, which is that dy by dx minus theta is equal to shear force in the cross section. So, that is a function of x V x divided by correction factor K G A, where A is the cross sectional area. But you see here we have got two kinematic variables y as well as theta, and we got just one equation. So, we have to look for another equation, and that is going to come from the moment curvature relationship. Okay. So, we have learned from the bending of beams that E I times the bending curvature, that is equal to the bending moment m, right. And while doing the Euler-Bernoulli beam theory, we said that the bending curvature is same as the curvature of the center line, right. But now we are also accounting for shear, is not it. So, it turns out when you account for shear, then the bending curvature is no more equal to the curvature of the center line. So, we can make that remark here that bending curvature is no more equal to the curvature of the center line. Since the center line is also undergoing shear. Okay. So, that means your curvature kappa is not equal to d2y by dx2, but we can relate curvature kappa to the cross sectional rotation. Let me tell you how. So, recall the bending of beam when the beam turns into a circle. And then this radius is big R, and here is your neutral axis. Now, look at the rotation of the cross section. For example, if I concentrate on this cross section and the cross section over here, the relative rotation of the two cross sections is same as this angle here, is not it? So, what can you say about the rate of change of angle with respect to the arc length x? So, what can we say about d theta by dx? So, we know because it is a circle, then r into d theta would be same as the arc, is not it, which in this case is dx, because we are saying that the center line is not undergoing any stretch. So, the initial length of the center line and the final length of the center line is the same. For example, this arc is dx and the angle if that is your d theta, then the two cross sections here the relative rotation of those two cross sections is d theta and the arc is dx, the original distance between the two cross sections. So, this relationship holds, which implies that d theta by dx is actually 1 by r, and that is your bending curvature. So, we can say that E I into d theta by dx is equal to bending moment m of x. Okay. So, this is more general. See, in case of Euler-Bernoulli theory, theta was equal to dy by dx, right. So, let us make a remark here for E B T, theta equals dy by dx. So, that means d theta by dx is equal to d2y by dx2, and that is the equation that we had, E I d2y by dx2 equal to m of x. But for Timoshenko beam theory, theta is not equal to dy by dx, and therefore, d theta by dx is not equal to d2y by dx2, which is the center line curvature. Okay. So, more accurate equation is this box here. All right. So, finally, we have gotten the two equations required for Timoshenko beam theory, and we can write them together. It is dy by dx minus theta is equal to shear force V x by correction factor k g a, and E I d theta by dx is equal to bending moment m of x, and it is a set of two equations, each of which are first order coupled system of equations each are first order. So, when you integrate it, you will require two boundary conditions for each of the variable that is appearing here. Y, the highest order is first dy by dx, there is no d2y by dx2 in this equation. Similarly, for theta, the highest order that is appearing here is d theta by dx. So, for each of the variable, the highest orders are 1 and 1. So, the number of constants that will appear due to this order will be 1 plus 1, that is 2, okay. And then you may require more constants depending on whether V x and m x also have got some unknown. So, I can make that remark here, because of y and theta having highest order of 1, we would require 1 plus 1, that is equal to 2 boundary conditions plus any extra boundary condition if V x and m x also have got unknowns. All right. Now, let us try to solve the simplest equation using Timoshenko beam theory. So, you can recall that we had solved this problem where the beam was clamped at one end and we were applying a transverse load at the other end P. So, we solved this using Euler-Bernoulli theory. This is called a cantilever problem. Now, we would like to solve it using Timoshenko beam theory and see how the results are differing. Okay. So, the first thing to do is we have to find the shear force and bending moment distribution V x and m x. So, to do that we will have to cut a section and look at the free body diagram of the cut part. So, we have one P acting here, and at the cut section we have shear force going downward V x and bending moment clockwise m x. Okay. Now, if we do moment balance about this green point, then we get minus m of x plus p into L minus x, because we are supposing that this length is x. So, this is equal to 0. So, that implies bending moment m of x is equal to p into L minus x, and then shear force, when you do force balance, you would get V of x is simply equal to p. All right. So, we can plug in these two formula in our equation, and then we get E I d theta by dx is equal to p into L minus x, and the other one is dy by dx minus theta is equal to V x, which is p divided by correction factor k g a. All right. Let us now integrate the two equations. So, if we integrate this, we get theta equal to p by E I into L x minus x square by 2 plus an integrating constant C 1, right. Now, we can use the boundary condition. So, what boundary condition exists here? So, at the clamped end over here, since it is clamped, so the displacement y of 0 is equal to 0, and also because the whole cross section is clamped. So, cross section cannot rotate. So, that means theta of 0 is equal to 0. So, you should not say that dy by dx is equal to 0, because dy by dx is no more denoting rotation of the cross section. We have theta as an independent variable to denote cross sectional rotation. All right. So, when we substitute here that theta of 0 is equal to 0, so C 1 goes away. Okay. So, we can now plug in this formula in this equation over here and again integrate. So, we have dy by dx equal to p by E I into Lx minus x square by 2 plus p by correction factor k g a. So, this implies y, the deflection, is equal to p by E I into Lx square by 2 minus x cube by 6 plus p x by k g a plus the integrating constant C 2, and again because y of 0 is equal to 0, so that boundary condition simply tells us that C 2 is also 0. So, that is the formula for the deflection of beam, and notice the extra term that we have gotten here. So, this is the extra term. So, we have got additional deflection in the beam because of accounting for shear in the cross section. All right. Now, can we try to find out in what situations should we use Euler-Bernoulli theory and in what situations should we use Timoshenko beam theory? So, if the result from Timoshenko beam theory is very close to Euler-Bernoulli beam theory, then we can simply use Euler-Bernoulli theory, is not it, and neglect the effect of shear. So, let us see when the two results are same. So, from Timoshenko beam theory, what is the tip deflection? What is y L from Timoshenko beam theory? So, if you substitute x equal to L over here, we get P L cube over 3 E I plus P L over correction factor k g a, whereas y of L from Euler-Bernoulli theory, that is simply P L cube over 3 E I. So, if we find out what is the error in Euler-Bernoulli theory, assuming that Timoshenko beam theory is giving me more accurate result. So, the error, let us say epsilon r in Euler-Bernoulli theory would simply be y L T B T minus y L E B T, and if you divide by y L E B T, then you get relative error, is not it. So, this is relative error. Okay, and when we substitute the formula, we have P L by k g a divided by P L cube by 3 E I. Okay. And we want that the relative error to be very, very small, correct. So, we want that this should be much less than 1. If that is the case, then we can use Euler-Bernoulli theory. If the relative error is high, that means we should go for Timoshenko beam theory. Okay. So, let us try to find out what condition we obtain from here. So, we can cancel this P, we can also cancel this L, and this becomes 2, right. So, finally, we have 3 E I divided by k g a into L square much less than 1, right. See this I, that is your I z z, second moment of area. So, we could also write I z z as area into the radius of gyration square. So, R g square, correct. And what does this R g denote? So, that is going to denote the extent of the beam in the y direction, is not it? So, if we have got a rectangular cross section, then we know that this is H and this is B. So, I z z is 1 by 12 B h cube, which we could also write as B h into h square by 12, and B h is the area. So, area times h by root 12 whole square. So, h by root 12, that is your R g. So, it is proportional to the extent of the beam in the y direction, because that is your y direction and that is your z direction. All right. So, if we plug in that here, we have 3 E into area into R g whole square divided by k g a into L square much less than 1. So, this a goes away. This also implies that 3 E over k g times R g over L whole square is much less than 1, which finally implies, if you bring this on the other side, then L by R g is much greater than square root of 3 E over k g, right. And if it is an isotropic beam, then we know that g is equal to E over 2 times 1 plus nu. So, let us substitute that here, and this implies L by R g should be much greater than square root of 6 times 1 plus nu divided by the correction factor k. So, what we have here on the left hand side, we have length and R g, which is denoting the cross sectional dimension, right. So, it is denoting the aspect ratio. So, on the left hand side, this is denoting the aspect ratio, whereas on the right hand side we have got the material property nu. Of course, we also have got the correction factor k. So, k is a geometric property because it depends on the shape of the cross section, and nu is the material property. Okay. If it is a rectangular beam, k is equal to 2 by 3, and supposing that nu, the Poisson's ratio, for example, is 0.3. So, suppose that nu is 0.3, what is then right hand side equal to? So, we have square root of 6 times 1.3 divided by k, which is 2 by 3, right. So, that is square root of 9 into 1.3. So, that is somewhat close to, let us say, 4. is not it? So, if your L by R g is much greater than 4, so if the aspect ratio is let us say 10, then you can use Euler-Bernoulli theory. If the aspect ratio is let us say 4 itself, then you should use Timoshenko beam theory, right. All right. So, that is about Timoshenko beam theory. You can accordingly solve all the problems that we solved in the last class using Euler-Bernoulli beam theory. All that you have to remember is that whenever you talk of cross sectional rotation, then it is not dy by dx, it is theta itself. Okay. So, never say that theta is equal to dy by dx for Timoshenko beam theory. All right. There is another very interesting topic that we would like to cover today, that is called buckling of beams. So, all of you can do this experiment actually. Think of taking a long beam, it could be a stick from your broom. Okay. So, the stick is also quite long. So, take some part of that stick and try to compress that stick and see what you observe. So, if you apply very small compression, you will see that it is remaining straight, but then as you start increasing the compressive force, it is going to suddenly bend. So, the bending would be very sudden. So, initially there will be no bending, but only when you apply critical compressive force, then your stick bends, and that is called buckling. So, buckling is a sudden phenomena. Okay. So, supposing you have got a beam, which in this case could be your stick of your broom, and hold it from both the sides and apply compressive force. So, as you increase the compressive force and it reaches a critical value, then the beam is suddenly going to buckle. Beam buckles suddenly. So, buckling here means bends suddenly when the compressive force reaches a critical value. So, this is very interesting phenomena, and whenever we design any machines, if it has got a beam and it is under a compressive load, so we will always like that the compressive load is less than the buckling compressive load. So, if in the operational condition the compressive force that acts on that part of the beam or that part of the machine which is a beam, then you see that it is suddenly going to buckle, machine is going to fail. So, whenever you design your machines, you have to make sure that the buckling load is more than the operational load of the machine, only then it is not going to buckle. All right. So, let us see how we can obtain buckling load of a beam, and we will do what is called column buckling in this class, and we will use Euler-Bernoulli beam theory to model the beam. So, we are going to neglect the effect of shear, which means our beam is quite long. So, L by D, the aspect ratio is of the order of 10, 15, 20 or higher. Okay. So, column buckling means you have a column which implies it is clamped at one end, but at the other end you are applying a force, compressive force P, and as you increase this compressive force P, initially the beam is simply going to compress. So, its length is going to shorten, but at a critical point when the P reaches a critical value, the beam, instead of compressing, it will bend, and that is called buckling. Okay. So, we want to understand, or we want to find out what is that critical value of P at which this column is going to buckle. Okay. So, we have to first find the bending moment profile. So, let us suppose the beam has buckled or it has bent, and we have this force P acting here. So, to find bending moment at any x, we have to cut a section of the beam and analyze the cut part of the beam. So, we have this force P here, and at this cross section we have shear force acting downward V of x, then axial force, and we also have bending moment M of x, correct. And if we find out moment balance about this green point, then we have minus M of x plus the moment due to this load P, and how much is that going to be? You see, it is P times this length, the vertical length, which is the difference of the deflection of the tip and the cross section at x. So, that is y of L minus y of x. So, we have minus M of x plus P into y of L minus y of x, okay, and that is equal to 0. So, this implies M of x is equal to P into y L minus y, all right. So, finally, we can substitute that in our equation, and we have E I d2 y by dx 2 plus P times y is equal to P into y of L. Okay. So, the equation that we have here, it is a second order equation, and it is also non homogeneous, second order non homogeneous, because the right hand side is not equal to 0. So, we have to find its solution. To find solution for a non homogeneous equation, we have to first find the complementary part and then add the particular integral, and that is how we get the general solution, correct. So, to get the complementary part, we get the solution of the homogeneous equation first. Okay. So, the homogeneous part is E I d2 y by dx 2 plus P y equal to 0, and notice that this P here is positive. Look at this load here, it is acting towards the beam. So, it is already compressive. For a positive P it is compressive, for a negative P it will become tensile. So, we are going to substitute now y equal to e to the power lambda x in this equation, and so we get lambda square e to the power lambda x plus P by E I into e to the power lambda x equal to 0. So, that means lambda square plus P by E I is equal to 0, which implies lambda is equal to plus minus iota I square root of P by E I, correct, where I is your imaginary number. So, that is your imaginary number. So, whenever your lambda is imaginary, the solution has got cosine and sine part, is not it. So, the solution is simply y equal to some constant C1 times cosine of square root of P by E I into x plus C2 times sine into square root of P by E I into x. Okay. So, this is your complementary solution, and what is the particular integral? So, in this case it turns out when you substitute y equal to y L in the differential equation here, it satisfies the equation. So, any solution or any function, if it satisfies the differential equation, that can be your particular integral. So, here y equals y of L satisfies this equation. So, therefore, general solution is y equals C1 times cosine of square root of p by E I into x plus C2 times sine into square root of p by E I into x plus y of L. Okay. So, that is your general solution, and we have two integrating constants C1 and C2, for which we have to apply the boundary condition. So, in this case it is clamped at x equal to 0. So, our boundary condition is y of 0 equal to 0 and theta of 0, which is equal to dy by dx, because we are using Euler-Bernoulli theory. So, that is also equal to 0, correct. So, let us plug in these boundary conditions and see what we get. So, what is y prime, for example? So, y prime is nothing but minus C1 into square root of p by E I times sine of this number plus C2 into square root of p I times cosine of that number, right. And when we substitute x equal to 0 here, sine of 0 becomes 0 and cosine of 0 becomes 1. So, that means C2 into square root of p by E I is equal to y prime of 0, which is equal to 0 in this case, which means C2 is 0, right. And then we have to find out C1. So, to get C1 we have to say that y of 0 is equal to 0. So, we come back to our general solution with C2 being 0. So, we have y of 0 is equal to C1 times cosine of 0, which is 1. So, we have C1 plus YL, that is equal to 0, which implies C1 is minus of YL, right. So, finally, when we plug it in that equation, our solution becomes y of x equal to YL into 1 minus cosine of square root of p by E I into x. Okay. So, that is the solution. See, we have to find out this load p. So, that is the unknown. What is the load at which it is buckling? So, when it buckles, it has bent. So, our solution is actually for buckling. It is not for the straight line solution when the beam has simply compressed, because we are accounting for y here, is not it, which is the deflection of the beam. Okay. Now, to get p, you can simply set x equal to L in this equation. So, set x equal to L here, and we obtain on the left hand side it is y of L, which is y L equal to y L into 1 minus cosine of square root of p by E I into L, right. And so, y L cancels on both the sides, and this finally implies that cosine of square root of p by E I into L is actually equal to 0, correct. So, this implies that the argument of cosine, which is square root of p by E I into L, must be equal to odd multiple of pi by 2, right, because cos of something is equal to 0 when you have cos of pi by 2, cos of 3 pi by 2, cos of 5 pi by 2, cos of 7 pi by 2, right. Whenever you have even multiple of pi by 2, cos of 0, cos of pi, cos of 2 pi, 3 pi, 4 pi, they are all even multiples of pi by 2. So, there it is either 1 or minus 1, but for odd multiples of pi by 2 it is 0 always. So, this is equal to some 2 n plus 1 into pi by 2, where n is integer, correct. So, from here we get what should be this load P. So, this implies this load P is actually 2 n plus 1 pi by 2 whole square into E I over L square. So, that is the formula for your buckling load. Okay. So, there are actually many buckling loads. You set different n's, n equal to 0, n equal to 1, 2, 3, 4, 5, 6, you get those buckling loads. And what is the smallest buckling load? That is when n is equal to 0. So, for n equal to 0, we obtain smallest buckling load, which is your P critical. So, that is equal to pi square E I over 4 L square. Okay. So, that is the formula for the buckling load. Okay. Whenever you have a beam, it is clamped on one end and you are applying a compressive force. If that compressive force is more than this formula here, then the beam is going to bend. Okay. But if it is less than this formula, then it is simply going to compress. All right. And you see this number is proportional to E I, but inversely proportional to square of length. So, if your beam is even larger, if you have a longer beam, you require less force to buckle it. And you can again do that experiment with your stick of your broom. Take a shorter stick, take a longer stick, hold it at one end and push it from the other end. You will see that to bend the stick, you require lesser force when it is longer. When the stick is short, you take a very short stick and you apply the force, you will need lot of force to bend it, but with a longer stick, even a small force is going to bend it, and that is because of this formula that L square is in the denominator. Okay. So, this was the buckling load for column buckling, in which case one end is clamped and on the other end you are applying a force. So, this actually depends on boundary condition, right. You see, when you found this solution, the integrating constants C 1 and C 2, you got them by applying boundary condition. If you apply different kind of boundary condition, for example, when you have a beam which is clamped at both the ends, okay, and then you compress it. So, whenever you are compressing it, you are not letting the beam to rotate. In the column buckling case, right here, only one end is clamped. So, it cannot rotate over there, but at the other end the cross section can rotate. But in this picture down here, when both the ends are clamped, neither of the ends can rotate. Okay. And then again the question is how much compressive force can this hold before it buckles. When you do this analysis the way we did it now, it turns out that P critical here is 4 pi square E I over L square, and again it is inversely proportional to length square. Okay. So, when you change the boundary condition, your constants of buckling load changes, but the quality that it is proportional to E I or it is inversely proportional to length square, that is still there. Okay. In this case it is going to buckle in this way, okay, whereas in the earlier case, in case of column buckling, it is simply going to buckle in this way, and it is all because of the boundary condition. Okay. So, I hope you got some idea about buckling of beams. So, with this we close our discussion on beam theory. All right. Thank you.